Hello and welcome back, and hi if you're here for the first time. In the previous video, we talked about recurrent neural networks and LSTMs and how they were designed to process sequences of text. We saw that RNNs struggled with remembering information across long sequences, and LSTMs tried to solve that problem using memory cells and gates. If you haven't watched that video, please feel free to go and watch it. That was a major improvement, but LSTMs still had an important limitation. They process text sequentially, one word at a time. So if a sentence has 10 words, the model processes word 1, then word 2, and then word 3, and so on. This makes the training slower, and it also makes it harder to capture relationships between words that are far apart in the sentence. Researchers started asking a different question. What if we removed recurrence entirely and allowed every word to directly interact with every other word? Obviously, with few more important improvements. This idea led to a new architecture introduced in 2017 in a famous paper titled "Attention is All You Need." That architecture is called the transformers. And today, it forms as the foundation of most modern AI systems, including all the models that you might know, for example, GPT, BERT, and pretty much all the other generative AI systems. So in this video, we are going to carefully walk through how the transformer architecture works step by step. And this is the important part because this is the basis and the foundation of all the things that you're going to learn ahead. So let's get straight into it. Before we dive into the individual components, it's important to understand the big picture of how a transformer works. The original transformer architecture consists of two main parts, an encoder and a decoder. The encoder reads and processes the input text, building a rich representation of its meaning. The decoder then uses that representation to generate the output sequence. This architecture was originally designed for tasks like machine translation. For example, imagine we want to translate a sentence to French, "The cat sat on the mat." The encoder processes the entire sentence and produces an internal representation, a mathematical representation that captures its meaning. The decoder then uses that representation to generate the translated sentence word by word. So conceptually, the system looks like this: the input sentence, then the encoder, contextual representation, decoder, and then the output sentence. Now something interesting happened later. Different models started using only parts of this architecture. Like models like BERT use only the encoder architecture. Models like GPT use only the decoder architecture. We'll be talking a lot more about this. But all of them are still built from the same fundamental building called the transformer layer. Inside both the encoder and decoder, we stack many of these layers on top of each other. Each layer gradually refines the understanding of the sentence. Early layers might learn like simple grammatical patterns. Later layers learn deeper semantic relationships between the words. At a high level, the pipeline looks like this. It's text, then tokens, then embeddings, positional encoding, transformer layers, and final output. Again, we'll be getting into details. At the core mechanism that allows transformers to understand relationships between the words with something called attention. Before we go there, we need to convert the text into numbers. And don't worry about all of these terms. We'll be going through this slowly, little by little, explaining all these individual terms. Now, neural networks cannot understand raw text. They only operate on numbers. So the first step is to convert a sentence into something a neural network can understand. So we convert the sentence into tokens. For example, consider the sentence, "The cat sat on the mat." Now, this sentence might be broken down into tokens. We call this tokenization, which could be simply words or even set of words, like actually subset of entire word. For simplicity, let's just assume these tokens are words, but again, they might not always be words. But again, let's consider the cat sat on the mat, all of these individual words as tokens for now. Each token is then converted into a vector of numbers. This is the process we call embedding. There are different models that are actually trained to just do this part, convert text into embeddings. These words are converted into embeddings. You can think of these embeddings as kind of numerical expression or representation of a word. For example, the word cat might be represented as a vector, something like minus 0.2, minus 0.4, 0.7, 0.1, and many more numbers. In real models, these vectors can have hundreds or even thousands of dimensions, meaning an array of 1,000 different numbers. These numbers are not random. Models that I was talking about, which actually are trained, during training, they learn the embeddings such as these words with similar meanings end up with similar vectors. That's the logic and the magic behind it. For example, words like cat and dog and lion may all end up relatively close to each other in this entire vector space, while something unrelated like a car would be far away. This allows the model to capture relationships between words in a mathematical way, something that it can actually understand. However, there is still one problem. Embeddings represent meaning, but they do not always represent the word order. That is what we're going to look next into. So consider these two sentences. Dog bites man and man bites dog. Simple two sentences. They contain the exact same words, but the meaning is actually very different. If we only use embeddings, the transformers would see the same set of vectors, not exactly the same set of vectors, but still kind of similar vectors for both the sentences, without knowing which word came first. Embeddings do resolve this, but not in the sense that transformers can really benefit it. So to resolve this problem, transformers add something called positional encoding. Positional encoding gives the model information about where each word appears in the sentence. In the original transformer paper, position encodings were generated using sine and cosine functions. Going long way back, if you remember from mathematics, sine and cosine functions produce smooth wave patterns that repeat over time. For example, if you plot sine x as x increases, the values rise and fall in a regular wave. The transformer uses these waves with different frequencies to actually encode positions of words in a sentence. Each dimension, each index of your positional encoding vector uses a sine or cosine wave with a different wavelength. It's as simple as that. Because these frequencies differ, every position in the sentence ends up with a unique pattern of numbers. This has a very useful property. It allows the model to easily learn the relationships between those positions. For example, the model can learn patterns like this word is 3 positions after another word, or these two words are kind of very close together. So finally, these positional encoding vectors are added to the word embedding vectors which we just talked about. So each token, each small token, which could be a word, which could be a part of the word, that's a complete separate kind of process. Each token now contains both the information about its meaning and information about its position in the sentence. If you want to know more about how tokenization works, just let me know and we could create a video about it. For now, let's move ahead. Now we arrive at the most important idea in the transformer architecture, which is self-attention. This is one of the most important concepts. Self-attention allows each word in a sentence to look at every other word and kind of decide which ones are relevant. It's very important, and if you're not able to understand from this video, make sure to understand this from the Attention is All You Need paper itself. Now let's look at this particular sentence. The animal didn't cross the road because it was tired. When humans read this sentence, we naturally understand that the word it refers to animal. But how does a neural network figure that out? How does it figures it out mathematically? Self-attention solves this by allowing the word it to compare itself with every other word in the same sentence. To make this work, every word is transformed into 3 different vectors. Remember, vectors. Every word is represented in a vector form. Now these vectors are called query, that's the first one, key, that's the second one, and value, that's the third one. You can think of these as a kind of search process. The query represents what word is looking for, what the word is actually that we're looking for. The key represents what information a word contains. So you're looking at a particular word, that's your query. All the other words are basically keys. That's the information a word contains. The value represents the information that word contributes in the overall sentence. So understand the meaning difference between value and key there. So when the model processes the word it, its query might implicitly represent to something like, I'm looking for a noun that this pronoun refers to, right? So other words in the sentence advertise their keys, right? So each word basically would have a key. They're kind of throwing in, this is the information we have. It is the query word. And then the model compares the query vector, the vector for the word it, that's for one word, with all the other key vectors in the sentence. So the word it is kind of matched with all the other words in the same sentence with their keys. To measure how similar two vectors are, the transformer uses something called the dot product. This is another small mathematical concept, but extremely useful in data science generally, and especially in this self-attention process. If you imagine vectors as arrows in space, the dot product measures how aligned those two arrows are. Like if these two arrows are in space of vectors, then these arrows, if they're very close to each other, means they're very similar. So if two vectors point in the same direction, the dot product becomes large, right? If they point in very different directions, the dot product actually becomes very small. So the dot product essentially measures the similarity between the query and the key vectors. Dot product has a very simple formula. Make sure you can see that online if you're actually going deeper into the mathematics, but it's not rocket science. So this produces a set of numbers called attention scores. Each score represents how relevant one word is to all the other words, right? And this happens for all the words, right? So for all the words, you have their attention scores with respect to all the other words in the same sentence. So what happens next? These attention scores are then converted into weights using a function called softmax. There are a lot of functions like sigmoid, softmax, and many other, but softmax takes a list of numbers and converts them into probabilities that basically sum to 1. So basically you have different numbers, they are converted into probabilities so that the overall sum equals 1. For example, if the scores are 2, 1, and 0, softmax might convert them into something like 0.65, 0.24, and 0.11. It's basically another way to represent the numbers, but in the sense of probabilities, so that we can know how much probability each word is throwing, but their overall effect contributed is basically equal to 1. So this tells the model how much attention to give to each different word. Before applying softmax, the scores are divided by the square root of the vector dimension. This is important because this scaling step prevents the numbers from becoming way too large. So without scaling, softmax function would become extremely sharp causing the model to focus too heavily on one single word, which is not what we want. We want it to actually look at all the other words, right? So dividing by the square root of the dimension, dimension is basically the size of your vector arrays, right? So dividing by the square root of the dimension keeps the values in a stable range, allowing the model to learn a bit more smoothly, if that makes sense. Once we have these attention weights, the model combines the value vectors. Remember, so far we have the attention scores using the keys and the query vectors. Now we have the value vectors as well. So you can think of this as computed a weighted average of the value vectors. Words that receive higher attention weights contribute more strongly to the final representation. So if the word it assigns high attention to animal, then the information from animal will strongly influence the representation of the word it. And that's how it actually learns what contributes to what other word and how they all contribute everything in a given sentence. So this entire process is summarized by the attention equation. Attention, or QKV, basically the three vectors that contribute in the overall attention, equals softmax of Q multiplied by K transpose divided by the square root of your dimension of K multiplied by the vector V. It's complicated, but if you actually think about each component, it starts to make a lot of sense. Despite the complex notation, that's why I'm saying the idea is rather simple. Each word gathers information from the words that are most relevant to it, and that's basically the basis of self-attention or the attention mechanism. But here's another important concept. Instead of performing this attention process once, transformers perform it multiple times in parallel. That's why they're also very strong, because they can do things in parallel. Each parallel attention computation is called a head, right? So there's one computation, that's one head, there's another computation, that's two heads, and so on. Different heads learn to focus on different types of relationships. So one head, one computation of attention might focus on grammatical structure. Another head might basically track pronouns, for example. So each of these heads learn different patterns. Another head, the third head maybe, might capture long-range dependencies in the sentence, like how one word is related to all the other words that are really long in a long range. The outputs of all of these heads are then combined to produce a richer representation of that one sentence. This process is basically called multi-head attention instead of a single head attention. And that is what transformers use to understand the patterns, to understand how the actual word mean inside the sentence as completed. So after the attention step gathers contextual information, the representation of each token is passed through a feed-forward neural network. Now this is a simple feed-forward neural network. If you want to learn more about this, we already have a video about it, so go and check that out. So this network processes each token independently. Each token, again, could be the word itself, could be part of the word in terms of its vector representation. The reason this works is that the attention has already allowed tokens to exchange information with each other. So the feed-forward network can now transform each token representation into a more complex feature representation. That's what now matters at this stage in the model. But there's another question. How do these scale so well? How are these layers over layers in this entire neural network so stable, right? So to make this training stable, transformers use two techniques. These are called residual connections and layer normalization. Residual connections allow information to flow across layers by adding the original input back to the output of the layer. Understand this because it's not that complicated. It basically allows the information that has been collected to actually go back to the output and so that it has a comprehensive view. Layer normalization keeps these values inside the network well scaled by normalizing them across a consistent mean and variance so that the values are not so spread that it becomes very difficult for the model to actually understand patterns. So together, these techniques make it possible to train very deep networks, and that's what is used in transformers itself. These are general concepts that are there in any deep learning networks, but it's important to understand or at least be familiar with these when you are trying to understand transformers. So to summarize the entire pipeline of transformers, right? Words are first converted into embeddings, the numerical vector representations. Positional encodings then add information about the word in order. How do they actually come in order? Self-attention, which is the next step, allows words to gather information from other words. But self-attention is not one head. Multi-headed attention captures multiple types of relationships and patterns. Then a feed-forward layer transforms these representations. Residual connections and normalization stabilize these trainings, and by stacking many of these layers together, the decoders and the encoders, transformers become powerful enough to understand and generate human language. And this architecture forms the foundation of modern generative AI systems. Stay tuned, because in the next video, we are going to learn something which is actually practical and which would actually help you implement stuff. We'll be learning about what prompts are, how do you actually work with LLMs, how do you prompt LLMs, because you already know the basics. This theory is actually very important to understand how things work. But now that you have familiarity with it, we can go and actually implement something. We'll be seeing how prompts work, what exactly is prompting, and we'll talk much more about what prompts are. So stay tuned, and thank you for being here. We'll see you next time very soon. Till then, goodbye and cheers.